So it all starts with the Lewis dot diagram. I mean, that becomes the backbone of how we're going to build these. And it's going to be the same thing with the covalent compounds too, except those are a bit of a nightmare. So if we look at these two here, let's say I just want us to draw the Lewis dot diagram for beryllium. Well, remember that Lewis dot diagrams, they're only interested in the electrons that are involved in bond making, right, or a chemical reaction. In that case, that would be the valence electrons. So when we draw our Lewis dot diagrams, it's just going to be for valence only. So beryllium, if you look at your periodic table, okay, it has, and we can figure out in terms of the group number, beryllium Be should be in group 2, okay? And so it has 2 valence electrons. So we're going to draw the B here, okay? And then we can draw the 2 electrons really anywhere. So some people do north and south. You could also do it like this. It really doesn't matter, okay? As long as I see 2 distinct electrons, and then that's it. That's the Lewis dot diagram for this thing here. Now, for the oxide ion, whenever we see the word "ide," that tells us, I should say, that it's an anion. So it's an element or an ion that has a negative charge. So if we look at our periodic table, we would see that oxygen has a charge of 2-. So when it's an ion, right, it's a 2- charge, and that 2- means that it gains 2 electrons, right? So I would circle that, gains 2. Now, oxygen is in group 16, which means that if we subtract from 10, we get 6 valence electrons. So normally, if I were to draw oxygen here, I would just have O with 1, north, south, east, west, north, south, and I just repeat it here. Okay, that would be normal oxygen, but I have to show it gaining 2 electrons. So these empty domains are going to now be filled with 2 extra electrons. So 1 in that domain and 1 in that domain. And now my ion is full, right? It has a stable octet. So what we do is, to indicate an ion, we put this in brackets, and then we write the charge outside, and then that's the complete Lewis dot diagram for an oxide ion. So again, just kind of a recap, when you're drawing a regular element or an ion, this is how we do it here. So only the ions are in brackets. Now that's going to be true when we incorporate this into the ionic compounds as well. For ionic compounds, we simply draw the Lewis dot diagram for each element in there. But it's an ionic compound, right? So when it comes to ionic compounds, it's filled with ions. That's why we call it ionic compound, right? So what's more of a real accurate description is draw a Lewis dot for each ion, because I should see brackets for the ions. So you would draw the Lewis dot for each ion, and then you're going to combine the 2 ions, in some cases 3 ions, using turning subscripts into coefficients. And we'll kind of show you what that looks like. So you can draw these in 2 ways. So if I have calcium fluoride, so I've got to break this into its ions. So that would be calcium. If you look at the periodic table, it's 2+. And then your fluorine would be fluoride, it'd be F-. So when I look at my Lewis dot diagram, well, that 2+ tells me, since it's positive, that it's going to lose 2 electrons. And then this is negative is going to gain an electron. So the original calcium diagram, we're looking at step 1 here. The original calcium diagram is going to be like this, right? You would have 1 electron, 2 electrons. But because this is a calcium ion and we're going to lose those 2, I would actually erase that. And then I'm going to put it in brackets and then the charge outside the bracket. So that would be the Lewis dot diagram for calcium ion. Now for fluorine, it's in group 7. So I would do this accordingly: north, south, east, west, north, south, east. I repeat until I have 7. But that gain of electron in that empty domain, and we fill up each electron domain with 2. And that has to do with Hund's rule and principles later on in chemistry, but like an upspin and a downspin, but that's much later on. So I've taken that electron, I've put it now here into that other domain, and then we're going to put brackets around it and write a minus. Now, to show that I'm combining them, right? So here I'll just put a comma between them. Now to combine them, which I'll do over here, you could do it in 2 ways. Both ways are fine. So the first way that I could do this is I could write the cation in the middle. So I would go Ca2 plus, okay? And then on each side, I'm going to draw a fluorine, or fluoride ion. Just like this. Charges included in everything. Let me just do it again here. Okay. So that's one way, and that'd be the complete diagram. So the cation in the middle, each anion on both sides. Or sometimes what people do is this. Okay, I've actually seen this drawn 3 ways. I'm going to show you the most common ways. So some people take the ion that occurs more than once. So in this case, that'd be the fluorine. They draw it first, so they go, and then they put a coefficient of 2 in front of it, indicating that there's 2 of them, right? Because of that subscript. Okay, and then they draw the calcium ion next to it. Both are fine. Okay, if you see another video that they're doing it like this, that's totally fine. If you see another video where they're going like this, again, both of them work. They both say the same thing. Let's get off at this here. Okay, so we've got aluminum chloride for our next example here. So same thing. We're going to separate this into ions. So I got Al3 plus and I got Cl minus. That 3 plus tells us it's going to lose 3 electrons. And then that Cl minus tells us it's going to gain. So same thing. I would draw my original aluminum would look like this, right? 3 electrons. But since it's an ion and it's losing those 3 here, okay? And then chlorine, again, originally it's in group 17. So it's going to have 7 valence electrons. Okay, so it would gain 1, and then that would just, again, go in brackets. Okay, so now this has 3 chlorines. I find for the bigger one here, I find it's probably easier to just go Cl with the 8 electrons around it here, Al 3 plus, and then just put the coefficient. Okay, just like that. But you could also, again, just do this. So you both are valid. Okay, just do whichever one makes the most sense. Okay, so let's say now for this question, it has one more little step. We have to get the right formula first of magnesium phosphide, which will lead us to Mg3 and then P2. And then the rest is the same. We'll draw each ion out, then put them together and make these subscripts turn into coefficients.